Let's move on to temperature. And before I can get to that, and let me give you a little introduction on energy, because some people seem to have still big problems with the word energy. They want to introduce energy at all costs into the discussion, and temperature has something to do with energy. So it's a good way of getting to the word temperature by going through energy. Okay, so here's one fellow, and he says the following. Okay, gives you an idea of what these people are thinking before, or how they use the word energy in order to get other things done. But we have to destroy the word energy before we can get there, because we need to understand the word energy if they're going to be using this word every 2 seconds. We need to understand what that is. Okay, so a fellow says, weight is a measure of the pull of gravity. By the way, this is part of the same thing. Okay, it's also weight and mass, etc. We have weight, mass, energy, work, force, all these, and field. Okay, all these words are esoteric words. You know, they're words that mathematical physics has invented, and these people just use them liberally without really focusing on what is being said. Okay, because they're going to try to give physical interpretations with these words. Okay, so this fellow says weight is a measure of the pull of gravity on an object. Okay, very clear. On Earth, the downward force of gravity gives an object a downward acceleration of about 9.8 meters per second square. Mass is a measure of how much matter there is in an object. All he did is just do cut and paste and put it up there. Okay, we need to answer the questions, not simply cut and paste and say this is what mass is, this is what weight is. We already have these definitions by memory. It's a poetry, poem. That's all it is. What we need to do is answer the questions. These are the questions that people who use the words mass and weight have to answer. So let's make sure we understand what the issues are and what people need to answer. Okay, here it is. Okay, we have is mass the quantity of matter? Yes or no? Okay, these are all yes or no questions that all religious, irrational folk need to answer, right? Is mass the quantity of matter? Does mass have anything to do with gravity? Okay, does mass have anything to do with speed? Because Einstein tells us that speed changes the mass of an object. Okay, and does the quantity of matter change with either gravity or with speed? And there you have the definition from the Wikipedia. Rest mass is an invariant quantity. Okay, what does invariant mean? It means it doesn't vary when it's at rest. So what are we talking about? Well, we're saying that the object has so many atoms. That's what they're saying. There's a quantity of atoms that forms something which we call the rest mass. Okay, fine. If that's the definition of mass, you cannot use it in the next sentence, which has to do with weight, which is what they call relativistic mass. It says is dependent on velocity. No, it can't be, because if mass is the quantity of atoms, the quantity of atoms does not change because something speeds up. So now they're talking about how that thing presses up against the scale. That's known as weight, not as mass. And so we have a problem because they're calling something which is known as weight, which it has to do with gravity or with pushing on a scale, and they're confusing that or using the word mass to define that. That's where the problem comes in. So this is what people have to answer. They have to answer, look, are we talking about mass or are we talking about weight? Okay? And so this is where we have a problem. These are the questions that people who use these words have to answer. They can't just continue to say, well, I'm just going to cut and paste and tell you that weight is this and mass is that. We already have that information. So there's no need to cut and paste anymore. Just answer the questions. Okay, and here Paul continues and it says the following. It says, work is equal to force times distance. The formula doesn't change because of incline or decline. Okay, again, it does change, and I don't take my word for it. Here are 3 sites that I pulled at random, and they all say the same thing. Yes, it does change. The equation does change, and here are the equations. The equation is force times distance times the cosine of theta. In other words, you're looking at the angle in which the thing is moving. It's not the same thing to push something straight horizontally as pushing it up a hill or down a hill. These are different. You have to perform different amount of work, pushing it up, straight ahead, or downwards. Okay, they don't. Why? Because you're helped by gravity. That's why. And so you need that angle. You need to know what the angle is. And here you have another fellow says the same thing. Okay, again, all these are equations. Okay, that these people put out there, and you can see that this one also mentions cosine of theta, and there you see it. What is theta? Is the angle between the vectors, force, and displacement, way down at the bottom. So you need that angle, okay? And here's a third one, okay? If I can get it here, okay? And this is from the Wikipedia. Okay, let me get myself back in here. Okay, this is from the Wikipedia, and again it says the force times distance times the cosine. Okay, you need that cosine in there if you're going to push up a hill or down a hill. So no, the equation is not force times distance. It's force times distance times theta. Now if theta is an angle of 0, then it comes down to 1, and so you have then it defaults to force times distance. So don't listen to this fellow, because you're going to be misled into how the equation is about the factor known as gravity that influences an object that is being pushed. Okay, gravity does have an effect on that, and so the equation really is with a cosine, not without it. Just be aware of that. Okay, moving on here. Let me get this out. Well, it says energy. Now we get to energy. Energy, the capacity. Defines it as the capacity. Okay, the definition, capacity to do work, is what? Conceptual. It's a concept, right? There is no physical object called capacity. Okay, capacity is a concept. Okay, no standalone physical object called capacity. Okay, but then this fellow continues, says energy starts the car, not the gas. So gas does not start your car. What starts it is this concept called capacity. And so capacity is what starts your car, not the gas. This is what people repeat without even thinking. These words have been shoved so much into their heads that they just parrot them, just say it. Oh, the energy that I have. And they use words of ordinary speech or notions of ordinary speech and introduce them into physics. No, hopefully in physics, it's gas that starts your car and not this concept called capacity, which he admits is a concept. Okay, and but he chases his tail around. He said, we don't start the car with thoughts, ideas. Right, you're right. And abstract conceptual is thoughts or ideas, correct. And so you don't start a car with concepts such as energy, because energy, as you said, is a concept. Okay, and again, all this comes down to big definition, the word object, that destroys all their arguments. Once you define the word object, all these religions go down the drain, and they hate it. They hate it because they've been educated and they have all these theories based on these words, and suddenly you say, well, that's not an object, you can't use it for a physical interpretation. And it just kills them. It just kills all their theories right there and then, because whatever they say, whatever comes out of their mouth is irrational. And so, yeah, they have a problem with that. Okay, and well, it says here, it says, we literally use 25 different energies, meaning that energy is not a physical object. And here you see, if you look it up in the Wikipedia, you'll find all these little ghosts. You have mechanical energy and gravitational energy and magnetic ionization, chemical. Then you have the rest energy. That's energy when you have rest mass, quantity of matter. Okay, chromodynamic energy, nuclear energy. Well, you have all these different kinds of energies. And today we're going to look at one of those at the bottom, known as radiant energy, because that's going to be the one that's going to create the heat, the temperature. Okay, so we're going to look at that radiant energy that these people talk about. Okay, and we'll get to that in a second here. But anyways, I just want you to know there's many kinds of energies, like saying flavors or maybe colors. The crayon is an object, but the colors of all these crayons is not an object. So if there are many energies, clearly energy is not a physical object again, okay? Because you have all these kinds of energy, mechanical and potential and kinetic and whatever. Obviously, energy is like an adjective. It's a type and not a thing in itself. Okay, so yeah, all these people have been brainwashed in high school, maybe in college, to think of energy as a thing, and they just took it for granted. Nobody even challenged that. And it's only when you put them against the wall that they realize that the mathematicians have created this concept and turned it into an object, because they give all the physical interpretations using the word energy, and people just use this word, like the word spirit in traditional religions, and they just keep talking about energy. What is this energy? What is this thingy? Please draw it. I want to see it. Okay, so let's review some of these things that I just mentioned here, primarily related to energy. But it says energy is the catch-all word of math phys. Okay, that's what it is. They use it for everything. Whenever you want to fill in a blank, in poker, or not so much in poker, but in rummy and whatever, you have this joker, and you can put it as any word, any card in there. Well, this is more or less what the word energy is. It's a joker, in every sense of the word. You can use it as any card you want. That's the problem with the word energy. because whenever you don't know something, you just say energy and you filled in the blank. That's the problem. And what did we learn when we use the word energy? In fact, it probably hides more than what it reveals. And no standalone object called energy. Energy is the capacity. And yeah, we have all these energies. When it's treated as an object, what you're doing is essentially saying spirit. The spirit. My car runs with a spirit. That's what this first person said. yeah, I believe it. Energy, according to mathematical physics, is equal to mass times one of those two, either velocity or the speed of light squared, right? Which one is it? Is it the velocity or the speed? And that takes us to what I covered a couple of weeks ago, where you have the velocity is when it changes, like when you have angular momentum, right? Speed, straight line, no problem. But velocity is no problem when it's in a straight line. But when you turn a corner, now you've had to accelerate. And the way they fixed that is saying, well, the speed did not change. What changed was the direction. And so direction is a qualitative concept. It's not a numerical concept. Therefore, they said, well, you have acceleration without an increase in speed. And so it's important because I'll tell you why. Because, you know, when Einstein says that you have warp space and you have this little photon that's going at 300,000 kilometers per second in a vacuum, and now it's going to go around the sun, it's going to turn a corner, it's going to change direction. Did it change its speed? Do we have a different value than 300,000 kilometers per second? And they say, no, the speed remained the same. What changed was the direction, okay? Because it's space that warped it, warped the path of that photon. That's the notion they have. And yeah, it has acceleration, but not because of speed, but rather because of a change in direction. That's the notion they have in mathematical physics. And that's important because, again, they're using acceleration to explain acceleration. Why? Because you have centripetal towards the center of the object, right? Where the center of gravity in this case. And what is that centripetal what? Centripetal acceleration, to explain why this thing changed direction, accelerated, but not because it changed its speed. When it changes its direction, why? Because you have centripetal acceleration. So we have acceleration to explain acceleration to explain acceleration. Great. That's the way the mathematicians fix this. Anyways, there you have a little a, acceleration, and again, no change in speed, it's change in direction. That's how they fix that. We're not talking really about direction, distance, we're talking about distance traveled. Again, I covered that the other day. Distance, the separation between two objects, that belongs to physics, whereas distance traveled is by one object, okay? And so it's distance traveled is very different than distance of physics. And then force, there's only two types of forces, push and pull. And what is not either push or pull is tension. Tension, no one wins the tug of war, and that contradicts the definition of force, which someone does win the tug of war. Okay, so all these things, keep those in mind. That's in general what I've covered. You can go back and look at some of the videos, and they'll bring you up to speed on what the arguments are in more detail. Okay, meanwhile, here we have electromagnetic radiation. We're going to talk about temperature today, and this is how it starts. And again, it's going to be related to energy. Energy, this spirit, this ghost, okay? And this is going to be radiation energy, okay? It consists of waves of the electromagnetic field. What the hell is a field? And I always like to say field is where the cows poop. That we all understand, that field, okay? But this field is what you see there. All these little vectors, as they're known, these little arrows that you see there, blue and red. And what do those represent? Well, they represent magnitude and direction. The arrow, that's why the arrowhead is there, right? Represents direction, but the height of each one of those arrows is representing a numerical value. Okay, so if you look at those blue arrows there, for example, the first little loop there, you got 4 arrows, right? You see short arrows, bigger arrow, and smaller arrow, right? Well, the smaller arrows represent a smaller magnitude, and the bigger arrows represent a bigger magnitude. That's what they're saying, okay? And you got to think of this in dynamic terms, like the wave is increasing or the field is increasing, and then it dies down, okay? Let me say that again, it's going to be important, okay? The field is increasing, and then it dies down. The field increases, then dies down. That's what they're saying, okay? Well, it seems like something that's turning, you know, like if you look at the blue one here, okay? Well, the field is increasing as you go from here to there, right? Because, see, it's fatter in the center, and as you get to the edges, right, it gets thinner. you can see, like, let me get it here. Okay, there. Okay, you can see what happens as you twist this thing around. Okay. Okay, this is what they're saying. They're saying that if you look at just the center here, what's happening? Suddenly it disappears from you and it becomes flatter. Okay, and here you see more of the blue. Here you see less of the blue. So the magnitude goes to 0 at some point, and here it's at maximum. Well, it looks like they're talking about a rope. Okay, maybe this vector thingy is just a rope that's torquing. Could it be? Okay. And yeah, it says linearly polarized sinusoidal electromagnetic wave propagating in the direction through a medium, such as the vacuum. The vacuum is a medium? What is a medium in mathematical physics? I thought vacuum was nothing, space, void. And now they're saying it's a medium. So the nothing suddenly becomes a medium. That's strange, that's weird. But it says the electric field, right, oscillates. Yeah, here it is. If the blue one, yeah, I think the blue one is the electric one. I'm not sure right now. But if the blue one oscillates, well, what do you mean oscillates? Is this what it's doing? See, here you have 0 electric field, and here you have maximum electric field. It's oscillating, right? And the same goes for the magnetic field, the red one. Okay, so what we have is maybe what we're staring at, that all those vectors going to 0, it's just something turning in situ. Okay, I mean, I can just as well mimic that with a rope. Okay, okay. Here we have the dynamic version of that. Okay, same thing. But see, they show it going straight and the thing increasing and decreasing. You can see that's all they're showing, that it increases and decreases. Maybe what they should have done is twirled it around like I did with a rope, and maybe that's a better representation of what they're trying to illustrate there. Okay, so the electromagnetic waves can be imagined as a self-propagating transverse oscillating wave of electric and magnetic fields. Well, the first problem is field. There's no physical object called field, because a field is just a bunch of vectors, and all that has to do with math and not with physics. That's the first issue. The second one is if it goes to maximum and then down to 0, maybe what we're talking about is something twirling in situ, in place. Okay, so this is what the argument's going to be. Okay, and of course, if we're going to relate that directly to temperature, let's continue here. We have this situation here, the definition of the word temperature. What is temperature? You look it up. This is from the Wikipedia. It says a physical quantity. A physical quantity? I thought physical, you know, under our definition, physical is the same thing as an object. Physical is that which has shape. That's what physical means in physics. Okay, so all these words, thing, object, physical, body, substance, entity, they all mean the same thing. Exactly the same thing. They're all synonyms, perfect synonyms. What is it? That which has shape. And quantity doesn't have shape. I don't know any quantity that has shape. Quantity is a concept. And so you either have concepts or you have objects. Okay, so quantity, physical quantity is a oxymoron. Okay, okay, but let's continue. It says expresses hot, meaning heat, right? And cold. That's what temperature does. And then what does temperature also have? The manifestation of thermal energy. That's what temperature is. Manifestation of thermal energy. Even though the word thermal means temperature. Okay, great. What is energy? The capacity. Remember? So it's the manifestation of thermal capacity. That's what temperature is. Okay? The source of the occurrence of heat, right, is matter. What is matter? Any substance that has mass. What is mass? Quantity of matter. Chasing the tail around. Heat, the flow of energy. And at that point, I guess you have to pass go and collect 200 and go back to energy and start all over. You know, it sounds like the Argentine PCR test. You go in a circle. Okay, so yeah, this is what you get. I mean, you know, what do we have here? Energy has something to do with heat. Heat has to do with matter. Matter is the amount of mass, or the something that has mass. What is mass? The quantity of matter. And what is heat? Energy. And then you go back to energy and start all over and say, oh, what is it? Okay. So all they did was go around in circles. We haven't learned anything with all these words that mathematical physicists use. Certainly, we cannot relate it to anything physical, which is what we do here. We do physics here. We don't do math. We don't care about math. We want to understand how this universe works. We need the mechanisms of how Mother Nature does her stuff out there. Okay, so here we go with temperature. They say it's related to the vibration of molecules or atoms or whatever the substance is made of. Okay, if matter is heated, its temperature rises more and more, okay? It can be seen that the particles contained in it move ever faster. Okay, no problem there. We're saying that the molecules, atoms, if you want, whatever the substance is made of, is vibrating faster. Why is it vibrating faster? What? Physical object, thing, physical, right? What thing is making the molecule move faster? That's what we want to understand. We're going to do physics here. We can't say, well, it just does, and here's the equation. We don't care about that. We want to know what physical object comes in contact with each one of those particles. And it turns out that, you know, when if you see it there, right, when you look at that, you see that all these atoms or molecules, whatever those are, they're all connected by a little line there. I hope I'm not the only one seeing some lines there. Do you see the lines connecting the balls? All of them? 100% of them? What are those lines? I looked it up in the standard model and I couldn't find lines. So I don't know what those lines are. Yeah, we all understand that if you move, you know, if you have two, let me move that for a second out of there. You have this situation, right? Two atoms bound by something that, you know, unites them, that binds them, that connects them. And this one moves, one of them, like the one on the right here, moves back and forth. This one's going to move probably in some way because of that. That we can all understand. Now try to do it this way, without the thing that interconnects them. Okay, so when I move this one, why would this one move? See, it doesn't move. But here, if I'm holding tight and that thing is straight, in fact, it's better to do it with my magic wand here, okay, because that's fixed, okay? So if this guy moves that way, this one has no choice but to follow, okay? So this is the one I'm going to move, okay? I'm going to move it to my right. And if I'm holding on to it, it's going to pull. We all understand that. And vice versa. If I pull on this one's going to move. But without that thing in between, you know, I can move this one and it doesn't affect this one at all. So yeah, the question that we have is, what are those, let me put this back in there, what are those little lines that they put between those alleged atoms or molecules? What are those lines? See, they put those things, you say, well, yeah, I understand that. Yeah, but you understand it, but that's because they put it there by hand. What are those little lines? Can you identify those things? Because obviously it's a thing. It's got at least 2 dimensions, I would say, maybe 3. Okay, so you got to identify those lines. That's the issue. Okay, and so this takes us to the spectrum, because they say that what that is has something to do with frequency. The freak of what? What freak is this? Okay, and here it is. Frequency is directly proportional to the average velocity of molecules. Okay, so that means if you increase the frequency, you're going to increase the average velocity of molecules. The higher the frequency, the hotter it is. The lower the frequency, the colder it is. Okay, but what is this frequency? The frequency of what is the question. Okay, this is what we want to understand. We want to understand the physics of this. Okay, so yeah, we see that, and here you see another version of that. Essentially, there you see it. It's the frequency of light, of this electric and magnetic fields. Okay, and again, what are we staring at? We're looking at a bunch of vectors. Okay, some are moving faster, the ones on the top, and those are identified as heat or hotter, and those are on the bottom moving slower, and those are identified with something that is cold. Okay, great. But what are those vectors? What are those arrows? Well, again, it's a bunch of arrows that form the so-called fields, and those vectors are just magnitude and direction. Magnitude and direction of what? What is it that we're talking about? What is this frequency, the thing that is going to move the molecules, the atoms or whatever that forms a substance that is heated up? We need to figure out what the objects are, the things that are moving the molecules. This is the issue. And so far we haven't learned anything about the physics of it. We've learned a lot of math, frequency, yeah, great. And what is frequency? Well, it's a bunch of vectors that move. Yeah, that's the field, etc. All these are concepts. We still don't understand what is moving this thing we call a molecule, this thing we call an atom. What is moving it? And what are those little lines that unite 2 atoms? Okay, because yeah, if you put the lines in there, you can understand why one shakes the other one. But what is that line? Is that just put in there to fool you into believing that one atom is moving the other one physically because there's something connecting them? Yeah, we can all understand that if that thing is real. But what is that? They don't identify that. They identify the balls that you see there, which are supposedly the atoms or the molecules. But they never identify the little connection there. What is that? Frequency? Is that a field? Is that light? Is that electricity? Magnetism? What is that little line? Okay, that's what we need to get down to. We need to identify that little line. Okay, and so here we go. This is what a so-called electromagnetic wave looks like. Maybe the red one is electric field and the blue one is magnetic field, or maybe it's the other way around. It doesn't really matter, just color codes. Okay, but what you're seeing here, if you stare at it a little while, you'll find out that the blue one is kind of moving around. It's going to values of 0 and then increasing to bigger values. And the same with the red one. You would think that when it goes down to a 0, what you're actually doing is just twirling something around. I mean, doesn't that look more or less like this one? Here you see them again. You'll see what happens here. Give it a second. You'll see what happens if we turn this into something else. Doesn't that look like that? When you're just twirling a rope. And here it is again. Yeah. Doesn't look like it's just torquing in place. That's all we're having. That's all we're seeing there. Okay. So here you see them, one compared against the other, so that you get an idea. Give me a second here. Okay, here you have it. Let me remove this one out of here. Okay, there you have it. Isn't that what you're seeing? It's not that it goes in one direction or in the other, it's just twirling in place. Okay, we have a representation using the rope for what these people call a wave, transverse wave, electric and magnetic fields. We say it's electric and magnetic threads. Okay, two threads that form a rope. They're physical, if we're going to do physics, right? Because otherwise you're doing math. Those vectors, that's not physics, that's math. They're magnitude and direction. So we can have the same mechanism that we've had for the last 100 or so years, 150 years, the famous transverse wave, the one that James Maxwell described mathematically. And we can just as well replace that with a rope and get the same result. Okay, so we don't need these so-called fields, whatever fields are. Okay, we don't need these vectors, whatever vectors are. Magnitude and directions only. No physical object, just magnitude and direction. Those are mathematical descriptions. And yeah, when you put the rope in there, now you can see why, this is true here. The velocity of light is equal to frequency times wavelength. Okay, and one exchanges with the other. The more you have, the more you torque it, okay, the more links you have for the same amount of rope. Okay, so here, for that same amount of rope, you have fewer links, and each link is longer, which is what you see there. And now here you have more links, and each link is shorter. That's what that equation says. And yeah, now we can relate it to temperature, because we can say, look, the longer the link, what we call the link length, not the wavelength, but the link length, the longer it is, the colder the substance. And the more torques you have, in other words, high frequency, as they call it, lots of links, each link being smaller, shorter, now you have higher temperature. So this temperature thingy, we can relate to the rope, because now we can say, well, yeah, if you have a higher frequency, like in the one on the bottom, the links are shorter, so that thing is moving quite fast. In other words, one little goosebump of those hits the atom much faster than the one on the top. The one on the top is moving slower in the sense that each link that arrives or that makes contact with an atom does not do it at the same rate as the one on the bottom. And now we can see why that would vibrate the atom in a lattice much faster than if you have a longer link. So this is from a physical point of view. You can now explain this. Okay, you can explain why this molecule or this atom, whichever of the two, because again, all molecules are interconnected with this rope. You can understand that, if you have this, and this is torquing. Remember, all this is at the speed of light. It's very extremely fast. Okay, compared to what we have in our macro world. Okay, so if you have this situation, you can see why this would be hotter than something that is like this, undone completely, and that's going to be a cold influence. In other words, a slow influence on an atom compared to this one. Okay, because this is a higher frequency, more links per unit of time or distance. So this is the issue. The issue is that One is going to give you more impetus, more impacts on an atom than the one that's got the longer link. And that would explain temperature. Whereas, in the case of mathematical physics, what physical object is coming in contact with the atom? And they draw those links. They put the little line, which is this, okay? We have something. We put a rope in there. What are they going to put in there? Are they going to put a vector? Are they going to put a field? Are they going to put a light? What physical object are they going to put between two atoms? What are those lines that form part of the crystal structure of, for example, a rock or whatever, quartz? What are those lines? And they never identify those. They might say it's a hydrogen bond. What is a bond? What do you mean a bond? Like James Bond or what? I mean, what is this bond? Is it a physical, is it an icicle, a string? What is it? And that's when they move to mathematics. They try to explain it mathematically. They just say, well, this is how it influences. It's a vector or who knows what word, esoteric word they put in there to fill in the blank. No, you have to identify the physical object. We're saying the object is a rope that interconnects any two atoms. The rope does have links, which is what these people call wavelength. We call it link length. More links, that's frequency. And now you can explain why one atom can influence another one and turn it into something hot, right? Because you have these higher frequency or more links getting to that atom than another influence, another rope that could have elongated links. That's the difference between them. And so, yeah, again, we have a physical mechanism, whereas mathematical physics does not. That's what it comes down to.